So, as I said, good afternoon. I hope you had a good lunchtime and relax. Yes. My name is Dr. Arranz, Dr. Paul Arranz, and I'll be teaching the solar module. Yes, and we have decided to start with a small session, yeah, on principles, technical principles, concepts. Yes, some things that will be important to remember throughout, during all this course. Okay, some of these concepts, you know them very well. Perhaps you have learned them many years ago. Okay, and now it's time to bring them back, yeah, to on the table, because some of these aspects will be important when we discuss, especially the calculation exercises, case studies, sizing, etc. Okay. So we start by remembering what are the energy units conversion. You remember in the energy sector, we can use different units to refer to the magnitude, the energy streams, the energy quantities that we are considering. Yeah, the international unit for energy is the joule. But of course, the joule can be also obtained by multiplications or considerations of other magnitudes. Yeah? It comes from a force being applied over a certain distance, so that's Newton per meter. At the same time, the Newton is a force, etc., so on and so forth. Yeah. Remember the difference between energy and power. Okay, power is the amount of energy being consumed or being produced over a certain period of time. This is why the correlation between joule and the unit of power, which is the watt, is 1 joule equivalent to 1 watt per second. Okay, that takes us to the second energy unit that is very typically used in energy engineering, which is the kilowatt hour. As you see, that is a unit of energy, even though the kilowatt is there. Okay, in this slide you can see the different conversion factors, yeah, to transform joules or megajoules in this case to kilowatt hour. Yeah? That's a very practical reference. Yes, for every kilowatt hour we have 3.6 megajoules. Okay. Other units are the tons of oil equivalent, very much used when we talk about primary energy, yes, and also the calories when we talk about or the tons of coal equivalent, or calories when we talk about heat. Okay, that's a very commonly used unit. Now, other basic aspects, yes, the forms of energy. Of course, there are many other forms of energy. This is just a selection of the energy forms that will be relevant for this training course, this capacity building course, yes. Electricity, heat, chemical energy. This is very important when we talk about biomass, bioenergy, yeah. Chemical energy understood as the energy that is stored inside the materials, yeah, inside the bones of any chemical compound. Potential energy, that is very important for hydroelectrics, and also kinetic energy, the energy that is due to the movement of a mass. Okay, so different forms of energy. As we will all remember from our from our perhaps the primary school, yes, we were taught that the energy is never created or destroyed, it's just being transformed all the time. Yes. Okay. Let's move on a little bit. Yeah, electricity. Remember, electricity, it is basically the flow of a charge, of an electrical charge around a certain circuit. And then this charge carries energy in the form of movement of electrons between atoms of different compounds. this circuit is normally materialized, okay, and the body, the shape of a conductor, of a body, of a solid body, we call it conductor. Even though electricity can also be generated and flowing, yeah, through some other media, but normally it's solid elements that we call conductors. Okay. Okay, the electrical charge is the fundamental quantity of electricity. It is measured in another unit called the coulomb, okay, which is the electrical charge of found in the electrons, okay. The electrical current is the electric charge rate, okay, which moves from one point to another per unit time. The electrical current, that is also sometimes known as intensity, that is measured in amperes, okay? It's like the flow, okay, of electricity. And as a convention, we adopt positive and negative. Positive describes the direction of the electricity current flow opposite to the movement of electrons. If you remember from the electricity basic lessons you received, sometimes electricity flow, it is explained as the movement of the electronic holes that are left by the electrons when they move, okay? The next magnitude to remember is the voltage. The voltage is an expression of potential energy. In this case, the potential difference between 2 points. The formal definition of electric voltage, if you remember, is the work, that is energy, required to move 1 coulomb of electrical charge from one point to another, okay? So we define the voltage between one point, at a higher voltage, to another point, a lower voltage. Absolute voltages are always measured with respect to a reference voltage, okay? Which is very often referred to ground or voltage 0. Different types of electric current. This is very much relevant for photovoltaics. Those of you who are already familiar with PV modules, with photovoltaic modules, yes, and batteries, you will remember that they mostly operate with direct current, okay? That is also known as galvanic current. That is, let's say, the natural electricity that is generated spontaneously by natural phenomena, like such as lightning, such as in our bodies, in our neuronal system, etc. And direct current is characterized by a unidirectional flow of electric charges, okay, and a constant intensity. As I mentioned before, this flow of charges travels through solid media typically, which is called a conductor, such as a metal wire, okay? But it could also be established through semiconductor or some other materials, or even in vacuum. Yeah? Typical DC sources that we are very familiar with are dry cell batteries or the photovoltaic panels, okay? The other type of electricity current, the alternating current, okay? Alternating current is artificially generated, by machines. It is characterized by changing over time, either in an intensity or direction of the flow at regular intervals, which we call the frequency. This is, of course, alternating current. It is because it has this changing over time. There is a moment in which the power being transmitted through a conductor, there is a moment where the power is equal to 0. This is why distributing electricity in alternating form is safer with comparison to direct current. This is one of the reasons why alternating current was invented, let's say. Okay, most of our appliances are supplied, are ready to work, to operate with alternating current, AC, as opposed to direct current, DC. In Mozambique, like in most of countries in Europe, the AC standard voltage is 220 volts for low voltage single phase, and the standard frequency is 50 hertz. That is that in every second there is this change of direction of the alternating current in a second 50 times. Okay, that is the meaning of a frequency. And in this drawing here, I don't know if you can see my arrow, my mouse, we can see what are the forms, yeah, of voltage throughout time. In direct current, the voltage will be constant over time. In alternating current, we have this wave form, okay, typical from alternating current. And in here we can see the cycles. The one whole wave is one cycle, and when we mention the frequency of the alternating current, means how many cycles we have per second. Okay, now let's remember the most basic fundamental equations in electricity. This is important for the calculation, the sizing of the generation, okay, in photovoltaic projects. Yes, the amount of electric current that will be flowing through a conductor, through a wire, yes, is proportional to the voltage, and it is inversely proportional to the resistance between those 2 points. This resistance is due to the material, yeah, and every material, every conductor has an intrinsic resistance. Okay. In a way, the resistance, if you remember, was defined to us as the opposition, okay, that materials create to the flow of electric current. And due to this opposition, you will remember there is always an effect of generation of heat and a bit of loss of the energy, electrical energy being transported in that wire or in that conductor. Resistors can be connected in series, okay, and then the overall resistance of a series of resistors will be the addition of all of them. At the same time, resistors can also be connected in parallel, and then the resulting resistance, have to follow the same formula, is the addition of the inverse fraction of each resistor. Okay. When we connect resistors in the same circuit or in the same wire, we get the effect that resistors in series will create an addition of voltage. The voltages being lost in each of the resistors will need to be added, and the intensity or the current flowing in one same line of resistors in series, this current will be constant. Whereas when we connect resistors in parallel, the voltage between point A and B will be constant, and the current flowing from A to B will be the addition of the different currents flowing through each of the resistors. Okay. Then we move on to Watt's law. That's the next important law, equation that we need to remember. And Watt's law is very important because it states the relationship between electric power, current, voltage, and the resistance that it is found in a certain circuit. You will remember Watt's law states that power equals to the multiplication of voltage times the current. If we remember that voltage and current are related by the resistor, then we can also introduce in these equations the resistor factor. So this is a very important law that we use, for instance, to understand how PV panels, PV modules will be working in our in the PV system we want to design. We'll go through all of this in the practical examples we will do in the next sessions in this course. In terms of alternating current, what we are saying is that the AC flow periodically changes its direction. The voltage is varying between the maximum and minimum values in every cycle. It is positive half the time and negative the other half. Okay, as I said, the frequency of this changing in the voltage happens 50 times per second. These are the equations that explain, the function of voltage over time. And since it is a waveform, we are using the equivalent in geometric is a geometric function using the sinus function of time. Okay, with the angular frequency, the amplitude of the wave, and the period, which is the time that one whole wave needs to repeat itself. Now going to some more practical aspects of AC, of alternating current. We find two types of main, apart from resistors, or two types of resistors that are found in alternating current, which are the inductors and the capacitors. You will remember, inductors are also known as coils or inductances. They are very important for inverters and for transformers, obviously. Inductors are passive electronic components that store energy in the form of a magnetic field. Okay. The inductors, they measure the capacity, the magnitude, sorry, of an inductor is measured. It is named as inductance, and it is measured in standard units of henries. Okay, with the symbol H. A capacitor is a device that stores energy in the electric field that is established between a pair of conductors that are charged with opposite electric charges. Okay. Capacitance, which is the magnitude or the ability of a capacitor to collect and to store energy, is measured in farads. Okay, a unit for capacitors is farads, and the unit is simplified with an F. Okay, the common word to refer to resistance in the amount of resistance in an alternating current circuit, it is the word used is impedance, which includes inductors or capacitors. Okay, we can also mention or refer to them as inductive resistivity or capacitive resistivity. Okay, and here we have the equations that help us understanding and measure alternating current. Yeah, as opposed to DC power, if you remember Watt's law, because of the changing, in the direction of magnitude of voltage, in the power consideration of in an AC circuit, we need to factor in this changeability of the voltage wave. So we need to include the waveform, and the most simple equation we have for that is to include the cosinus of the angle phi or phi, which is the angle between the active power and the apparent power. Okay. This is very important because depending on the type of appliance that we are considering, appliances, depending on how they are built and how their conductors are set up, will have this angle here will be bigger or smaller. meaning that this cosinus will be closer to 1 or closer to 0. This is important because the higher this cosinus, the smaller this angle will be, the higher the efficiency we will have in this alternating current circuit. If you remember all of this, in the end, we have to remember that we should always try to design and to work with appliances that has cosinus as closest to 1 as possible, so that the working power, as opposed to the reactive power, is maximized. Okay, and we don't waste part of the power in the circuit in magnetizing power in our capacitors or in our inductors. Okay, here we have a chart of the typical power factors. This parameter here, cosinus of phi, is known as the power factor. Okay, this table here tells us which kind of typical power factors we can find in motors, lamps, ovens, welding machines, etc. You can see in some appliances there is a bit of a wide possibility. Like in welding machines, we can have welding motor generator gensets that can have power factors from 0.7 to 0.9. So whenever possible, we should try to use and consider generator sets with higher power factors, because we will be able to draw the maximum of working power from that machine. Okay, so remember about the power factor. Then to conclude this section, remember also, in order to optimize the distribution, the transport of electricity in alternating current, we use three-phase, tri-phase transport fashions. Three-phase power circuit consists of 4 wires, 3 for each phase together with a neutral. And then the alternating current, which is carried by each wire, has the equal voltage in amplitude and frequency. That is, of course, an ideal three-phase power circuit. Then we will see that that is not always the situation in real working operation conditions. Yes. Three-phase distribution is very much appreciated in residential lines, or also, when we start considering industrial consumption and where the power starts increasing, and we need to redistribute this power being transported across different customers or very high consuming customers. Okay. In terms of materials, remember we have different materials being part of the electrical installations. We have conductors, we have semiconductors or insulators. This each type of material has a specific function in electricity design or electricity engineering. Of course, conductors are the main media by which electricity flow is being transported, and typically we use materials like gold or mostly copper or brass, etc. Then we have semiconductors, which are less conductive. They have a bit more of resistivity than conductors. Okay, and they are also of interest in the PV industry. Tomorrow we will explain a little bit more what is the importance of semiconductors for the generation of the photoelectric effect, mainly silicon. And finally, we have insulators. Of course, insulators are materials that protect, that block the conduction of electricity flow. And they are very much used in our designs because they can help us to block or to direct to protect the conductors and to block or redirect the flow to prevent from damaging our installations or our appliances. This is very generic, yeah, description, but the idea of this talk is just to probably, go back to some of these old lessons we took many years ago and have them a bit fresh for what is going to come in all the next presentations and training sessions we will have. Finally, I'm about to conclude. We, apart from electricity, of course, in these training sessions, we will be dealing with another big form of energy, which is heat or cold sometimes, but mostly heat, coming from Bart's sessions on bioenergy. So when we refer to thermal energy, we have some other principles and key aspects that you should remember, starting by the heating values, in fuels, normally measured in megajoules per kilogram or gigajoules per ton. Essentially, we have the gross calorific value, also known as higher heating value. Okay, that is the total calorific energy. This is chemical energy, which is stored, remember, in the bonds, molecularly, if in each of the bonds of the chemical composition of each fuel. Which the higher heating value includes the latent heat of evaporation of the water that will be produced during combustion, plus the water that is already present in the fuel. Okay, in bioenergy, as Bart will explain to you, to be able to extract the energy from biomass, we need to burn it. Yes, so when we burn biomass, we will always be releasing. We need to dry it and we need to release the water, the moisture content that is happens to be in that particular biomass. Okay, so when we get rid of the water, then we can consider what we call the net calorific value or the lower heating value. That is precisely the useful calorific energy in that biomass or in that fuel. Okay, because that doesn't consider the energy we need to use to evaporate the water there. Most commonly form or nomenclature used is NCV, and in this table we have some examples. We can compare what is the calorific value, net calorific value, and the gross calorific value of different fuels. Coal, diesel, butane, these are all, of course, fossil fuels, compared to wood, type of wood, which is eucalyptus tree, already dry, so with a very low content of water, of moisture. You can see very obviously that biomass, natural wood, has much lower net calorific value than some of the fossil fuels. But of course, biomass is a renewable source and fossil fuels are not. Another way of understanding the net calorific value in a more graphical form, yes, you can have these examples that Bart has prepared for us. The net calorific value, it is not, it depends from which biomass, from biomass to biomass. It will depend on the biomass composition, particularly the amount of ash and the different molecular composition of each biomasses, but most especially on the moisture. Wet biomass, of course, we will need a lot of energy to get it dry and to be able to extract the chemical energy. We will need a lot of energy to get rid of the water, of the moisture. Okay, so whenever I think the bottom line of this is that whenever we consider a biomass, we always need to ask ourselves or be worried about what is the moisture content at which these calorific values are being referred to. Okay, and Bart has prepared this example for us. Here we can see that in a kilogram of wood that eventually has a moisture content of 40%. Yes, yeah, we would need we would need, we can only extract, 11 megajoules of energy out of 1 kilogram of wood, okay? Whereas that kilogram of wood, imagine that kilogram of wood was much drier, moisture content much lower, 15% compared to the 40% here. From that kilogram of wood, we could extract 15.7 megajoules. So you see, from one same kilogram of wood, how important the moisture content it is. Because the amount of energy we can obtain from 1 kilogram of wood is very different if the moisture content is 40% or 15%. As a quick and easy, as a rule of thumb for woody biomass, you can consider the equation here. Net calorific value in megajoules per kilogram is 18.5 minus 21 times the moisture contents in percentage. Okay. Finally, to close this review of principles, of technical concepts, a very quick look at the physics of hydropower. Professor Dr. Divas will be, of course, talking to you this weeks about hydropower, how to design hydropower systems, etc. And for that, we need to remember the key power equation in hydroelectric science. Hydropower technology deals mostly with the potential energy of a water source, and that water source is characterized by its head and its flow rate, the mass flow rate, which is converted into kinetic energy that water will be moving and will be hitting, will be spinning a wheel, a turbine, that it is coupled to an electricity generator. So this equation, remember, it correlates the power of a hydroelectric site or system. It depends on the efficiency of the whole setup, the density of the fluid, normally it is water, so we use the density of water, the acceleration of gravity of this water in movement, falling from one height to another height. This is the head, the height difference between the 2 points where the water is flowing or is moving. And finally, the flow rate, the amount of water, the volume of water that is moving per unit of time. The flow rate is measured in cubic meters per second or cubic meters per day, etc. You have here all the references that we have used in this presentation. And yes, I will leave it here as an introduction, as a remembering. I'm sure most, if not all, of these concepts, you had already learned them, perhaps many years ago, yes, and some of them, if not all of them, will be used in the coming sessions to design, etc. Don't worry if there is something that you didn't fully understand now in this presentation. When it comes to the point in the exercises we will do, we will always revisit them if necessary and explain them again.